So these are some worked solutions for questions 5 and 6 from exercise 13.5 from the Year 1 textbook on the chapter on logs and exponentials, and in particular on the section on modelling curves. Don't copy the answers to these before you've actually had a go at the questions yourself. Question 5, part 1, we're given this formula for the number of trees, which is equal to k multiplied by a to the power of t, where t is the number of years after 1910. So our first job is to take logs of both sides. So ln of n equals ln of k a to the power of t. ln n equals ln of k plus ln of a to the power of t. So I've used a log rule here. Log of ab, a product, is equal to log of a plus log of b, which of course works in any base. Then we know that ln of n is equal to ln k plus, and then I can use another log rule here, so this becomes t ln a. Now later on we'll be comparing this to y equals mx plus c, equation of a straight line, so we're using the reduction of an exponential equation into its linear form via logarithms. So y equals c plus xm, if you want a direct comparison there. It's a bit of an odd way of writing it, but hopefully we can see that this is the y variable, this is the x variable, and then over here we have the y-intercept and then the gradient here. So part 2 asks us to make a table of values for t versus ln n. So we start at 1910, which of course is a time of 0, and then when we reach 1930, well, that's 20 years after 1910, 1950 is 40 years afterwards, and so on and so forth. Now we must be careful when calculating ln n. If you look at the table, for 1910, it gives you, against the number of trees, 3,200, but actually we need to multiply that number by 1,000 to get the true number of trees. Remember, it tells you in the question just underneath the table, the number of trees is measured in thousands. So here, when I calculate ln of n, I'm going to calculate ln of 3,200,000, not ln of 3,200. So here is our completed table. You may have rounded your values of ln n. Remember, you're going to have to plot these on a graph, so you are going to have to round and estimate as you plot them, depending on the accuracy of your graphing paper. So part 3, we're being asked to plot a graph of ln n versus t on the x-axis, like this. So here we have the plotted points and the line of best fit, which actually fits very nicely as a straight line through the points. I've used graphing software, Autograph, which is free to use online if you download it, to draw this for ease, and I've also used Autograph to calculate the gradient and y-intercept. If you were doing this by hand, remember when you're working out the gradient, do not use the existing points from the table, the coordinates you've plotted. Find 2 other points that you can, with relative ease, work out the coordinates of, and then draw in your right angle triangle from there. Please use a ruler when you do this. The bigger the right angle triangle you can draw, the less error there is in your estimate for the gradient. Now, Autograph has worked out that the gradient of my straight line is negative 0.01472, and my y-intercept is 14.99, so really probably you have found you've got a y-intercept of about 15. Now there will probably be some concern if your gradient looks to be slightly different or even drastically different. Don't worry about it too much. It is going to depend on your graph and how you've drawn it. Really, we're looking for you to demonstrate that you've used your graph as accurately as possible. Now, if this means you get a slightly different gradient value, well, actually, it may work out to be okay in the end. we'll have to have a look and see, but you must make sure you're applying the procedure correctly. So don't worry if your gradient is a little bit different to this. You should hopefully have a value that's negative for certain, and you should have quite a small value. As you can see, this is not a very steep straight line, so we are looking for a low value of gradient here. Now, we know from earlier on that the gradient is equal to ln A. So ln of A is equal to negative 0.01472, and A is then equal to e to the power of this number, which I can work out on my calculator, and I'm then going to store it in calculator memory A. So I get a value of 0.9853 ... for my value of A. Probably we're looking to see whether we can get a value for around about 1 here. So I might round that to 0.985 to 3 significant figures, but store the accurate value in your calculator. Now we know that the y-intercept is equal to ln k, so ln k is equal to 15. K is then equal to e to the power of 15, which if you work it out on your calculator comes to a very large number, 3269017.372. So that is to the nearest whole number 3,269,017. Again, store that value in a graphical calculator memory so it's ready to use. Now, this is the point at which I know some of you will probably have become a little bit anxious because you've got different values for k than the back of the book. Now, this is because, and I'll just do a little aside here, in the answers, what they have done is they have found their C value to be around about probably 15.03, and then when they work out K, so K equals e to the power of 15.03, they then get a K value which is this 3368573.7 ... which they have rounded to 3,400,000, which is where that answer comes from. And it's purely because slight differences in your value of the y-intercept will give you ever so slightly different values of k. This is not something that you should worry about. I know it makes people very anxious to get different answers to the back of the book, but this is how this process works. When you ultimately do exam questions on this, you will see when you look at mark schemes that there is a degree of tolerance allowed. Now, the last part of this question asks you to work out how many years is it, or what is the year, when the number of trees falls to 500,000. So n equals 500,000. So I'm going to use this version of the equation, ln n equals ln k plus t multiplied by ln a. Now, I'm going to use my full level of accuracy for my value of k and for my value of a. So I have ln 500,000 equals ln of k, which I'm going to use from a calculator memory, plus t ln of a. So I need to start by subtracting ln of k, which gives me negative 1.8776 ... and that is equal to t ln a. I then divide both sides by ln a. Again, I'm going to use my exact value from the calculator memory. And this gives me the time as 127.55 ... years. So this is 127.5 years after 1910. So that means to work out the actual year, we want to do 1910 plus this value, which of course gives us an answer of 2037.55, which rounds to 2038 to the nearest whole year. And again, I know this will have worried a number of you because you will have found that you got very different answers to the answer of 2005 in the back. So where did this answer of 2005 come from in the back of the book? So let's see where that answer has actually come from. So they have used the value of k as 3,400,000, and for the value of a, they've used the rounded value of 0.98 from the gradient. Now, if you go from here, let's subtract ln of 3,400,000 from both sides. We get negative 1.9169 ... equals t multiplied by ln of 0.98. So divide by ln of 0.98 and we find we get t equals 94.884 ... So this time the year will be, when we add this to 1910, 2004.88, which of course rounds to 2005 to the nearest whole year. So yes, you will get some very different values because you're dealing with logs and exponentials, where small changes can result in very large differences, but just show you're working very clearly, show how you have calculated your gradient, show how you have worked out your y-intercept. If you're using rounded values in the calculation later on, explain that you are using those rounded values. And again, please don't think entirely in terms of exam questions. Examiners are well aware of these issues. So for example, in an exam question, they may well tell you to use a rounded value of k and a rounded value of a to ensure that people end up with similar final answers. They will give you a bit more direction than you would find in a textbook. So question 6, we have a relationship r equals kt to the power of n, and we need to take logarithms of base 10 to both sides. So we don't need to write the base 10 here, we can just write log. So log r equals log of k multiplied by t to the power of n. Log r equals log k plus log of t to the power of n. Log r equals log k plus n multiplied by log of t. So again, if we compare with y equals mx plus c, y equals c plus mx. So our variables are on our y-axis log r and on our x-axis log t. Log k is our y-intercept and our gradient is equal to n. So the next part of the question asks us to complete the values of the table. So we end up with a table which is log r and log t. Now remember, in the table it's clear that the radius needs to be multiplied by 10 to the power of 5 before you actually work out the log. So for instance, if we look at the moon Tethys, we're given in the table a value of 2.9 for the radius, but in fact the r value actually equals 2.9 multiplied by 10 to the power of 5. So here's the completed values in the table with rounding to 2 decimal places. So we need to plot a graph of these values, and we're told to plot log of t on the horizontal axis and log of r on the vertical axis. So again, I've plotted the graph in autograph, and I'm going to use that to help me find the gradient and the y-intercept again. So we need to, in part 4, find the gradient. So autograph tells me that the gradient is equal to 0.6738. Again, you may have a different value to this. Again, check your procedure very, very carefully. Check that you have calculated the gradient accurately. You should have a value that is probably around about 0.6, so perhaps you might have 0.4, 0.7. These are similar values, so just look and see whether your value is reasonable. If you're getting values that are much bigger than 1, for instance even 1.5 or 2, that does suggest you may not have plotted your points accurately enough, you may not have calculated your gradient correctly. Now our y-intercept is equal to about 5.2. Autograph tells me it's 5.268. So you may well have 5.3, 5.4, a value a little bit like that. So we know that the gradient is equal to n. So this tells me that my n value is 0.674 to 3 significant figures. but C, the y-intercept, is equal to log k. So I need to raise both sides to the power, well, I need to raise 10 to the power of both sides to work out my value of k. So this gives me k equals, so let's round that to 185,353, let's say, to the nearest whole number for the moment. And again, as well as rounding these values, I may well store these in calculator memories just in case I need the full accuracy. Now this time in the answers, I note that they've given a value of 0.68 for n, which is very close to the value that we have, and their value for k is 180,000. And again, we have a very similar value. At the point at which you have these very large numbers, there will, small differences in the value of the y-intercept will create large differences in the value of k. But we're going to go ahead using our values and see how we get on with those. So we're now told that an unknown moon has an orbital radius of 1.4 times 10 to the power 5. I'm going to substitute that into this equation. So log to the base 10 of 1.4 multiplied by 10 to the power 5 equals, now our value of n was 0.6738 multiplied by log to the base 10 of t plus log k, and I'm going to use the value that I found for k previously. So we're going to rearrange this by subtracting log k first of all. So this gives me minus 0.1218, etc. equals 0.6738 log t. Let's divide by 0.6738. So I then get negative 0.1808 equals log the base 10 of t, so I need to carry out 10 to the power of the left hand side to be left with my value of t. Let's work that out. So I am left with a value of t of 0.6593 ... which rounds to 0.7 days to one decimal place, which this time is the answer in the back of the book. So hopefully these calculations have reassured some of you that if you do get slightly different values, yes, you will get different answers in the end. What you must do is show you're working very clearly, make sure you've calculated your gradient and y-intercept correctly. There may well be slight differences in your answers to the ones in the back of the textbook, but please be reassured that exam questions work very differently to try and reduce the amount of variation created by people plotting different graphs.